In this video, we're going to compute area within polar curves. And to start, let's contrast this with what we've seen previously in the course. Usually we integrate in a single direction, like the x direction or maybe the y direction. Um, we move a certain distance in x, we're accumulating area between a curve and the x-axis. It's based off of area of rectangles. With polar coordinates, we're going to take a different approach. We're going to base things off of areas of circles. I want you to imagine a piece of a curve like this one that I've got here traced out. And we rotate maybe from an angle 0 up towards pi over 2, sweeping area as we go in the shape of a sector of a circle. Okay, so let's think about area of a sector of a circle. It's a fraction of pi r squared. The fraction depends on the ratio between our rotation theta and a full rotation of 2 pi, hence theta over 2 pi times pi r squared, which simplifies down to 1/2 r squared theta. Maybe you remember this formula from a geometry class. Well, this gives us a hint as to what we're going to be integrating. We're going to integrate 1/2 r squared theta, although the theta behaves as x behaved in traditional integration. So we're going to see it as a d theta. Here's our formula. Integrating 1/2 r squared d theta will give us area within pieces of a curve. Because we are squaring our curve function r, we tended to have lots of squared trig functions show up in these calculations. So here's just a reminder that certain double angle identities are going to be pretty helpful throughout this unit. Got a link here to help us better visualize what I'm talking about. I'm going to flip over here. Yep. Some lag here. Here is a polar curve. The actual equation here would be r equals 1 plus 2 sine theta. I know it looks a little different in Desmos, but it's r equals 1 plus 2 sine theta. And imagine orienting yourself towards angle of 0. There's a little green dot on the curve in the direction of 0. And we start rotating an angle on the curve. We're looking between the curve and the origin at whatever angle we're situated at. And we're just sweeping through this area shaded in blue as we rotate. This is how we accumulate area with polar integrals. Okay. If you go far enough around, you get the entire shape. This one's a bit of a special case. We see some double shading, but more on that later. All right, let's get back to the notes here. A little bit of lag. Things to think about, determining bounds. What angle are we starting at? What angle are we ending at? Trace around your curve in a counterclockwise direction. Pay attention to which quadrants your curve is going through to help figure out what your angle bounds will be. We integrate along an outermost curve. We're going to get all the area between that curve and the origin. Eventually, we'll see intersections of curves. Those intersection points will often serve as boundaries for regions of area. They might help us determine bounds as well. And then, of course, we can set a function equal to 0 to find angles at which a function intersects the origin. That might be relevant at some point as well. Okay, next page. See a couple basic examples. I've got another hint up here. Imagining spokes, as in a bicycle wheel, from the origin out to the outermost boundary of your region. Drawing these can help you figure out if you have an outer and an inner curve. I'm looking at this first example, the yellow shaded area. If I start at the origin and extend a spoke out to the outermost boundary of my region, I'm actually traveling through an inner curve before I get to the outer. Okay, and if we see a phenomenon like that, we're going to do some subtraction. It's very much similar to washer method from per semester. Okay, what I'm really doing is finding the area of the outer circle and then subtracting the area of the unshaded inner circle. Right, so for this first example, area between r equals 6 and r equals 4, both circles. So we go 1/2 r squared d theta. This is a fairly simple r. It's just a constant. We're going all the way around the coordinate plane, the polar plane. So we're integrating from 0 to 2 pi. And we're subtracting outer minus inner. I can write it as two different integrals, or I could combine it into a single integral with the 1/2 factored out to the left. Okay. Like I said, that's a pretty simple one. You can see my work here. Try it on your own if you like. It should also match up with geometry techniques that you know from back in geometry. All right, so it's integral of outer minus inner if there happens to be an outer and an inner curve. The second example here is a bit more complicated. We've got a pink region bounded by 3 curves. Okay, there's theta equals pi over 4. That would be this red line. That's where we're sort of starting our rotation from. We've got r equals pi, which is this yellow circle, the radius of pi. And then r equals theta. We haven't seen a function like this yet. If you have r equaling a multiple of theta, you're going to get a spiral, which makes sense because as you rotate, your angle is increasing. Your distance from the origin will also increase and increase to make this spiral shape. So we're going to look at the pink region between these 3 curves. I'm rotating counterclockwise from this red line until I hit the intersection of the green and the yellow. All right, so I'm thinking about bounds. The red line represents pi over 4. That's where I'm going to start my bounds. My intersection of the yellow and the green would simply be the theta value where r equals pi and r equals theta coincide. So we could set those equal to each other, which essentially says it's when theta equals pi, and that's going to determine my upper bound. Okay. Between pi over 4 and pi, I'm imagining some spokes from the origin. There is clearly an outer and inner curve, so my integrand is going to involve some subtraction, resulting in 1/2 integral of pi squared, pi being the outer curve, minus theta squared. The inner curve is theta, is the spiral. All right, so I've got my answer here with calculator. I also showed how it would look if you worked it out without a calculator. It's possible, but the numbers are a bit yucky. All right, so that's the basics. Next slide, we're going to get into some slightly more complicated stuff. Still dealing with some lag here. There's a couple different families of curves that are fairly common, and there's some nuance here. There's some special cases. There's a lot to think about, so I'm trying my best to summarize important properties and rules. First curve family is Rose curves. These are polar curves such that r equals a constant times either cosine or sine of a multiple of theta and theta. And these curves tend to produce what looks like petals in various directions, hence the name a rose curve, like a flower. Okay. The tips of the petals would occur, if you think about it, the petal tips are the points furthest away from the origin, so that would mean they occur when r is maximized. How do you maximize a cosine or sine function? You start thinking about what angles you see cosine or sine maximized at. The coefficient out front, this A multiplier, will correspond to the length of the petal. Okay. We have to be careful though, because the number of petals can fluctuate depending on whether my multiplier n is even or odd. If n is odd, you're going to have n total petals. If n is even, there are 2 times n number of petals. Really, even with the odd n values, there's 2n petals, but the second half of those petals fall right on top of the first half, so you don't see distinct petals. The orientation of these curves differs also depending on if we had a cosine or sine function. Cosine is a bit easier to figure out because cosine is always maximized when you have an angle set to 0. So it doesn't even really matter what the n value is. You know you're going to have your first petal pointing directly out to the right. I see a cosine curve in the middle down at the bottom here. That first petal is in the direction of 0 degrees. Sine is a bit trickier because sine is maximized when you hit an angle of pi over 2, but theta might differ if we're setting n theta equal to pi over 2. Okay. So if we set n theta equal to pi over 2, we can work backwards to figure out what theta is. For example, if n was 3, kind of like this bottom right graph, I could set 3 theta equal to pi over 2, and I get that theta is pi over 6, and that's why we have a petal oriented in the direction of pi over 6. If you need to graph one of these freehand, usually you are orienting that first petal using these 2 rules, and then spacing out the various petal tips using this rule of thumb, 2 pi divided by the number of petals, because these petals are going to be equally distributed around the unit circle. Okay? If n equals 1, you get a special case. It would be a single petal, so it doesn't really look like a flower. In fact, it will look like a circle. This bottom left graph has n equals 1, and we get a circle. It's not centered at the origin any longer, okay, but it is a circle. As far as finding the area of these things, well, if we're going to have 2n total petals to measure, we should integrate from 0 to 2 pi. That will tend to always work. We just have to be careful because, as mentioned earlier, if n is odd, we don't have 2n petals. We only have n petals worth of area. So to account for that, you would have to either multiply your integral by 1/2, or alternatively, integrate only from 0 to pi. Either one of those techniques should work. All right. So let's take a look at these examples down below. R equals 4 sine theta. N is 1, hence 1 petal. It's sine, so that petal is oriented in the direction of pi over 2 is where we maximize sine. And the length of the petal is equal to this 4 multiplier out front. It ends up being the diameter of this circle. If I want to find the area within, I'm using our formula from the previous page of 1/2 r squared d theta, but I have an additional 1/2 multiplied on because n is odd. And if you work that through, you'll get an answer of 4 pi, which conveniently matches our geometry. Circle of radius 2 into pi r squared is going to get you also 4 pi. Middle example, 1/2 r squared d theta. Nothing really tricky here. It's got an even n value, hence it will have 2n petals, hence integrating from 0 to 2 pi is fine without any modification. Okay, it's cosine flavored, so the first petal is in the direction of 0 degrees. It's got a length of 3. Because there's going to be 4 petals, I know that the spacing between the petal tips is 90 degrees or pi over 2. All right, and I just threw that into nint to find my area of those 4 petals. Last example, 3 petals, lengths of 2. N is odd, so I've got an extra 1/2 multiplier to account for less petals than anticipated. Okay, not too much else to say there. Let's head to the next page and see the second major family of polar curves. These are called limasones. Still getting some lag here as far as I can tell. Limasone, you can see some of those shapes down below. The template for the formula is constant plus another constant times cosine or sine. Okay. These are generally pretty easy to graph by hand if you plug in the nice quadrantal theta values, because you get nice values of cosine and sine. Usually A and B are whole numbers with the ones that we see in this course. So you can plot a few points. And if you recognize the template here, you know the approximate shape in between those points to fill out the curve yourself. So these things are called limasones, but if A and B are equal to each other, these two constants in the formula, you'll end up with something like this bottom left graph with a dimple at the origin, and we tend to call these cardioids. The thought process being that it looks somewhat like a heart, right? If B multiplier is greater than the A constant, well, R will sometimes come out to be negative, right? If, let's say cosine is a -1, B times -1 versus A being positive, the negative outweighs the positive term, so R overall is negative. And when R is negative, we are moving backwards from the official direction, which creates this small inner loop that we see in these second two graphs down below. Excuse me. Now, if there is no inner loop, integrating these things is pretty straightforward. We just go 0 to 2 pi, 1/2 r squared d theta, no big deal. But if there is an inner loop, we have a little bit of a problem because that inner loop is going to get double counted if you integrate from 0 to 2 pi. I'm going to flip back to Desmos and show you this phenomenon here. Got this lag again as far as I can tell. My secondary screen, it's a little bit behind. Make sure it's caught up before I start talking. All right, so still need another moment here. There we go. If I start integrating this limasone from 0 towards 2 pi, I'm getting all the area between my curve and the origin. Okay. Still experiencing lag. I don't know if you can see what I'm seeing on my screen. I've got blue area shaded. I'm not seeing it on my secondary screen yet. There we go. All right, so we got this blue area, but as I start to rotate, we can see that inadvertently the inner loop starts to get covered before I've actually gotten there. All right. I'm just going to go ahead and move this forward a bit and hope that the screen catches up. But you could start to see it there. The blue area is covering up the inner loop. By the time I rotate far enough to hit the inner loop, and then I start rotating through the inner loop, I will be continuing to measure that area, but now I'm double counting it. That inner loop is getting counted a second time once my cursor moves back to the origin and starts traveling through that inner loop. Start to see it a little bit there in the video. Okay, so what do we do about that? Flipping back to my notes here. I'm not sure if you're seeing the lag. I'm pretty sure you're seeing the lag I'm seeing. It's a little bit unreal right now. Just gonna wait a second here. Go. So what happens is if we've got this inner loop, we have to find its area separately and subtract from the original calculation just to avoid double counting. Okay. Excuse me. As far as the bounds for the inner loop, well, we enter and exit this loop precisely when r gets back to 0. So if you set r equal to 0, we can find those bounds. All right. First example, bottom left. This one does not have an inner loop, so it's fairly straightforward. I simply integrate 0 to 2 pi, 1/2 r squared d theta. I threw it into n int to get an answer there. The second example does have an inner loop. So looking at the work below the picture, here's me setting r equal to 0, using a calculator to find the radian angles that represent the entrance and exit from the inner loop. And I've got those numbers down here. Moving up above, now here I'm doing the official calculation of the full area from 0 to 2 pi, which has double counted the inner loop. So after the fact, I'm subtracting a second integral using the bounds of the inner loop that I calculated earlier. Okay, that's how we go about it. We do have to be careful because sometimes you can set r equal to 0 and get some numbers to pop out, but you have to be careful about the order of them. I'm looking at this third example where we set 1 minus 2 cosine theta equal to 0. We get a couple angles, and yet it would be a mistake to subtract the inner loop by trying to integrate from pi over 3 to 5 pi over 3 because the entrance and the exit are flipped around. Pi over 3 is actually an exit from that inner loop, whereas 5 pi over 3 is the entrance. So the preferred way to deal with that is instead of using 5 pi over 3, that might have popped out of this calculation, you should be using negative pi over 3 so that you're only encompassing the inner loop itself and not the other portion of the curve. All right, so here is the actual calculation for that third example. All right, let's move on here. In the next slide, we start to look at the area within intersections of multiple curves. I'm still dealing with this lag, trying to wait for my screen to catch up. Here we go. Okay, you can see a picture down below. We've got a limestone in a circle. We're trying to find the area inside one curve, but outside the other. So some hints for these problems. When determining bounds, you want to trace around the intersection region in a counterclockwise direction. Pay attention to what quadrants you're using. You might see outer minus inner curve happening once again. The intersection points of the curve are typically going to be the bounds. Sometimes you need more than one integral. If you don't have a consistent outer and inner curve all the way through, if those roles change somehow, you might have to set up different integrals. And of course, we can also try to use symmetry to make things a little easier as well. All right, so this example, r equals 2 minus 2 sine theta, that would be the limestone pointing down. R equals 2 is a circle. Okay, if we rotate counterclockwise, there are two intersection points of these curves that appear to be the starting and ending point. And the shaded region that we want has the circle as the outside and the limestone as the inner curve. So all of that points to us setting the two curves equal, finding a couple bounds, and then integrating with 2 squared minus the whole limestone squared. That's going to give you that yellow area. Right. We've got, I think, 1 or 2 more examples on the next page. I'm a little nervous about this lag, but let's try to flip over to the next. Right. My mouse. Oh, there we go. All right, we're back. This next example is a fairly common setup. Got a couple circles. Really, they're rose curves, but they look like circles because it's a single petal, such that one is sine, one is cosine. We get this uh, sort of seed-shaped region of overlap. But we have to be careful with these because this is the phenomenon I was talking about a moment ago where your outer curve changes. You start at 0 and rotate around this shaded region. It appears that the yellow curve, the sine circle, is the outer curve if you imagine drawing spokes through here, up until the intersection point where we cross over. And now as I sweep the second portion of this thing, it's the green circle, the cosine circle, that's my outer curve. So what that tells us is we need to integrate the sine curve from 0 up until whatever our intersection is, and then a second integral from that same intersection back to pi over 2, which is where the green circle returns to the origin, since it's a cosine circle. I've got that work situated here. I used a calculator to find the angle intersection of 0.951 that shows up as an upper bound in one calculation and then a lower bound in the other. All right, so be prepared to do two separate integrals if you see this sort of trademark circle intersection problem. Okay. The last example is the most complicated. Maybe this is a bit above and beyond what we would need to worry about on a test, but just for fun, we've got two different rose curves. We want to find the area inside the sine curve, that would be the red one, but outside the blue cosine curve. There's a bunch of different strategies for this. Want to try to find something that makes sense to you intuitively. My approach here, I just took the entire area of the red curve first, used a calculator, and then I went through and counted up these tiny little regions that I need to subtract out. These like I have this yellow region here. There's actually 16 of these little yellow sliver regions in pairs of 2. And those are exactly the areas that I need to subtract out. I'm trying to find an area that's in the red, but not in the blue. So to find the area of just this single yellow highlighted section, I'm going 0 to pi over 8, that would be an intersection of the blue and the red. Finding that area, I need to subtract 16 copies of that from my previous total. Okay. There's other ways to do it, but that's the version that I showed that would be pretty quick with a calculator. Right. So I'm going to conclude the video there. Email me if you have questions. We'll have time to talk in class on Friday as well. Thanks for watching.